Hi everyone, my name is Ishan Mishra and welcome to my Explain Something project presentation for generators versus motors. So I wanted to begin by talking about why I relate with the subject. So first, I am a computer science major, which while I do not need to have an in-depth knowledge of hardware simply for the fact of using the hardware, does require me to have sort of a knowledge of how the hardware works so that I can possibly write software for it later on in my career. Another reason is that I love robotics. Robotics is a major part of my life. I've been into it since I was, very young. And motors are used ubiquitously in robotics. I mean, they're called servos, but they're what allow the actual robot to move in different degrees of motion. The concept of generators and motors are also ubiquitous in everyday life. They're used in cars, appliances, homes, power plants, turbines, etc. And as an example, you can see on the right a picture of a car engine, which applies the concept of motors to work. So we'll begin by talking about what generators are. So generators are machines that essentially convert mechanical energy into electrical energy through electromagnetic induction. And we're going to talk sort of more about the principles that actually allow for this electromagnetic induction later on, but I wanted to do just a general overview where a coil of wire is rotated in a magnetic field, which causes a change in magnetic flux and in turn generates an electric current. So this is used to generate electricity for various applications. I mean, they're used in power plants. They're and then sent to our homes. They're what power everything in our life. You know, and they're essential components in modern electrical systems. So an example of this is a DC generator. On the left, there is both AC and DC generators, depending on what type of current you want. For actually sending energy from the power plant to us, we need AC generation. But when it comes to things like charging your phones or something from an outlet, you would require DC current. So that's how those sort of generators differ. What are motors? So as you can see on the right, there's two diagrams that explain essentially how motors work. They're the exact opposite of generators, though. They turn electrical energy into mechanical energy through the same principle of electromagnetic induction. And basically, it works on a wire that experiences a current in a magnetic field, which causes it to move and generate rotational motion. And essentially, I'm going to talk about this more later on, but the direction of rotation can be determined using Fleming's left-hand rule. So motors have different features like speed, torque, and power. And again, I want to talk about the diagram on the right because you can see between two of the different poles, there is a wire that is rotated. And this essentially this magnetic field is what essentially causes it to move through electromagnetic induction. So just a closer look right there. So the physics principles behind generators and motors are what I'm going to talk about now. So the first one is we're just going to go one by one and talk about them. A few we're going to talk about how they actually apply to generators and motors, and a few we don't really need to go too heavily into except just explain the general definition. So the first is Lorentz force. The Lorentz force is the electromagnetic force experienced by a charged particle moving through an electromagnetic field, which results in its deflection perpendicular to both its velocity and the magnetic field direction. So this is in generators and motors, the Lorentz force is crucial because in a generator, when a conductor, usually like being a coil of wire, moves through a magnetic field, the Lorentz force acts on the charged particles within the conductor, inducing an electric current. So basically, this current is the basis for generating electricity. And in motors, the Lorentz force is used to create rotational motion. When a current flows through a conductor in a magnetic field, again, the coil wire, the resulting force causes the conductor to move, which drives the motion of the motor. Second one is Faraday's law of electromagnetic induction, which states that a change in magnetic flux through a closed loop of wire induces an electromotive force, an EMF, in the loop, leading to the generation of an electric current. So basically in generators, it's the principle that explains how mechanical energy, which is essentially the movement of the conductor, is converted into electrical energy. And the changing magnetic flux due to the rotating generators coils induces an electromotive force and it generates electric power. And in motors, the reverse process actually occurs. Like I said, they're the opposite of generators. The application of an electric current in the presence of a magnetic field generates mechanical motion. So that is the law of electromagnetic induction that essentially runs both generators and motors, except with reverse effects. And finally, we have, so in terms of things that are crucial, we have conservation of energy. So the conservation of energy principle asserts that energy cannot be created or destroyed in an isolated system, and it can only change form. So here we see generators change. Let me go back a slide. Let's talk about that. So we see that generators are machines that can convert mechanical energy into electrical energy, but they're still conserving that energy. And in motors, we see that the mechanical energy is produced by using electrical energy. So that's essentially what I mean by conservation of energy. And we can just do a quick overview of the other ones. Lenz's law states that the direction of an induced electromotive force or current in a closed circuit opposes the change in magnetic flux that produced it. Ampere's law relates the circulating magnetic field around a closed loop to the electric current passing through the loop, providing a quantitative link between the electricity and magnetism. And finally, the left-hand rule that I mentioned earlier is what we can use to sort of to actually determine the direction of the force that's experienced by the current carrying conductor in a magnetic field. So right here, how I said the direction of rotation can actually be determined using the Fleming's left-hand rule. And as you can see on the right, we have sort of an example of how a visual example of how electromagnetic induction works. And we kind of worked with a very small version of this in lab with the electromagnets. Let's talk about what analogy actually applies to generators. So the one that I came up with is that it can be explained like a water wheel in a river. A river flow pushes the water wheel in a circular motion, generating mechanical energy to do work. And so essentially this is how a coiled wire is rotated in a magnetic field, which generates electricity through induction. And this analogy also follows the conservation of energy, where the kinetic energy of the water running in the river is converted to rotational energy to actually move the water wheel, which does some work on something else. So on the left, you can see like a very basic diagram of a 3D diagram of how this would work in real life. In terms of motors, it's a very simple analogy. We can compare it to how our bodies use fuel from food to move in the same way that electrical energy is used in motors to convert into rotational motion. So essentially when we eat food, we get energy, which is converted to stored energy. And then that in turn is converted to mechanical energy when we need it. And so that mechanical energy is then used to, of course, move our arms, our legs, any form of movement that we need. And this also demonstrates the same conservation of energy that motors follow, which is the chemical reactions in food are converted to mechanical rotational energy that we use. So thank you very much for watching. As a quick summary, I wanted to just state that generators and motors are essential to our life in the world of post-industrial revolution. They are ubiquitous in our life. They mirror a lot of principles in nature as well as use them, such as the Faraday's law of electromagnetic induction, both forwards and backwards, conservation of energy. And they started from very simple conceptual discoveries that have now vastly evolved into things like generators that are used in power plants, to turbines, to motors for cars, etc. So it's fantastic to see how one small concept can grow into something very big. But yeah, thank you so much for watching. That was my explanation of generators and motors and how we can apply that to an analogy.